All right. So we're going to look real quick at the difference between ionic and covalent, and then you start to see some sort of blending between the two. And so that's kind of what this is going to talk about, is that there's like definitely covalent, there's definitely ionic, and there's kind of like in the middle. Okay, so um, here's just a little definition for electronegativity. So once again, like the measure of the ability to attract bonding electrons. So what does this mean? Does it want electrons? Does the atom want electrons? And so that's sort of the easy way to ask us that question. But some atoms and some elements just don't want electrons, and some definitely do. So if we look back at that chart over here, this chart of the electronegativity values, high values want them. So fluorine really wants electrons, and then low values like rubidium, they don't. And so it's just all about whether or not they want those electrons. And so that's kind of what you're seeing is chemicals that do and chemicals that don't. So electronegativity is just a tool that we can use to sort of predict or figure a few things out. So nonpolar covalent. So nonpolar covalent. So it means it's not polar. And so we haven't talked about polarity yet, but polarity basically, what that's going to mean is that it has poles. So think like a north and a south pole, or a positive end and a negative end. So if it's nonpolar, it doesn't have any charge at all. So like if you look at this oxygen, for example, this oxygen is completely identical on both sides, and so it doesn't have a positive end or a negative end. It doesn't have any charge at all. And so if I erase that and I make a water, the water has more electrons in the middle, in this area here. And so in the middle, your water is negative. So like kind of like a negative magnet. So the middle of this molecule is negative, or the top, if we look at the shapes, and then the sides are positive, like this. And it actually looks like this. Not a very good drawing there. It's actually a bent molecule, which we'll talk about in the future here. But it actually looks like this, so that negative is there on the top, and that positive is down here next to these guys. So anyway, that's polarity, and some things are not polar, so they just don't have a charge. They don't attract to things because magnets attract. So do of pluses and minuses, and so do atoms or molecules and things like that. And so these nonpolar chemicals, these nonpolar chemicals, um, they're not going to have any kind of attraction to to the electrons, and so all of the electrons are going to be shared, and so they're not going to pull electrons to one side or another. So this is going to be an equal attraction of electrons. So if I go back over to my water example, if we look, the oxygen is going to kind of hog up the electrons. So the electrons are going to kind of be up in this area. And so the electrons are going to slide to this area, which is why that area is going to be negative. And so if we use like a highlighter, we could kind of think that those electrons, they would be attracted to this area. And so you would see less electrons down here and more of the electrons up here, which is why that side ends up being negative. So these are examples, and you'll notice that they're all going to be diatomic. So nonpolar covalent is normally going to be totally identical chemicals or diatomic. Okay, so a polar covalent bond. So a polar covalent bond is going to be when it's still nonmetals, but it's got part of it is positive, part of it's negative, very much like the water, where this part up here is negative, and then this part down here is positive. That's going to be an unequal attraction of electrons, which creates a positive and a negative side. So polar covalent is going to be, instead of an equal attraction, it's going to be unequal. All right, so let's take a look at there. Here's some pictures. So ionic, we have an actual plus and an actual minus. And so we have in this situation, this over here is the plus. It's actually a plus. It has a plus charge, and because it pulled the electron to it. Now, in the middle, this polar covalent, it's non-metal, so they're not giving away electrons, but what happens is the electrons slide to the most electronegative end. So if you look at these examples here, like HF, HCl, HBr, so if you have HF, the electrons are going to be over here next to fluorine because it's the most electronegative element on the entire periodic table. So it's going to pull the electrons towards it. And the pure covalent is something that's like diatomic, like this. And so those electrons don't move around. They do move, but they are pulled in. Kind of think of like tug of war between two twins. There is no winner. It stays 100% equal. So, all right. And then D says that large differences in electronegativity values or numbers, which we talked about from the chart, they're going to indicate more ionic character, and that's the question they can ask about ionic character. So this is going to be more ionic character based upon whether or not that number is bigger or smaller. Okay, so large differences in electronegativity values are going to give you that more of that ionic character, and that's going to be in a bond, right? So anyway, the questions that you're going to normally see on a test are going to focus on just this, a test or a homework question. They focus on this. They talk about ionic character, and every year kids are like, ionic character, what the heck is that? It's just the difference in the two numbers from the chart, right? So don't get freaked out by that. All right, let's take a look at this question down here. Use the electronegativity differences to arrange the following bonds in order of increasing ionic character. So right away, where are we going to get these electronegativity differences? We are going to get them from the data book, right? These are not memorized. Like you have to know so much stuff for IB, but you don't have to memorize charts and tables. They're going to give those to you. So we're going to get this from the data book, the IB data booklet, which you get on all tests. And so on something for me, I'll probably just give it to you, let you use the book. So let's take a look. We have all of these. Now they're all C's, right? So we got to figure out the numbers for these. So we got to go back to that table. So we're going to slide over. So we got C. Let's go ahead and zoom in. So here's C, 2.6. And then I know there was a Cl, a 3.2. So let's go back, a 2.6. Now all of them are going to be that 2.6, right? So all of the carbons are the 2.6. So every one of them is the 2.6. And then we're going to have to figure out all of the other ones. So the chlorine is the 3.2. I'm going to put those in a different color. And then go back to the chart, and your hydrogen, go back to the chart. I'm just going to write it down because I've got it right here. So I got my chart pulled up. The hydrogen's 2.2 from the chart. The magnesium over on the left side is 1.3. The oxygen is 3.4. And the sulfur is 2.6. So notice right away that the the carbon and the sulfur actually have the same number. So what we do is we're just going to get our calculator out, and we're just going to just do a little bit of math. So we're just looking at the difference between these. So you want to make sure that you know how we're solving these. So, 3.2 minus 2.6 equals 0.6, right? So this one's 0.6, right? And so this next one, and I don't know if you need to write them all out, but it's just you might, forget. So 2.6 minus 2.2. So this one has a difference of 0.4. And I'm going to put those in a different color. Let's change this real quick. So we'll do blue. So this is a 0.6. And that one's a 0.4. And you guys can kind of get the idea, right? Like we're just sort of doing a little subtraction on all of these. So 2.6 minus 1.3. And then 2.6 and 3.4. So that's a 0.8. And then, of course, 2.6 minus 2.6 is 0. And I didn't write them all the math out for all of them, but you could write it all out. But just make sure that you did write some of the math down so you can kind of see them. So we're going to rank them. So kind of run out of space here. So we're supposed to go from low to high. So I'm going to go ahead and low to high. And then I'm going to rank them. So I'll use the yellow pen. So high is the big difference. Low is the small difference. So I'm going to put the low one on top. And then I'm going to work down. So the low one is the carbon-sulfur bond at 0. Right? And then it looks like the carbon-hydrogen bond at 0.4. And then the carbon-chlorine bond at 0.6, right? And then the carbon-oxygen bond. And then last, we're going to do the carbon-magnesium bond. I just kind of ran out of space there. So that would be the ranking. Maybe they ask you which one has the most ionic character, or maybe they ask you which one has the least. Well, you could do the same thing. And so obviously this would be the least, and this would be the most. And these are the kind of questions that you could see with ionic character. Once again, it's a kind of a silly vocabulary term, which is just like asking which of the chemicals has the biggest difference on that chart. So anyway, not hard question if you understand the vocabulary. Okay, writing Lewis structures, this is going to take a bit of time. I'm going to go through the whole thing, do a practice problem with you, kind of show you the differences from last year. Not that you are expected to remember last year, but we're going to kind of go through all of that. So I'm going to pause this one, and we're going to pick up here on the next video.